Hi, this is the Spectrum Analyzer project. To start off with, we'll do a quick demo. We'll jump somewhere louder. And we'll go ahead and we'll play something just a tidge louder, something in the electronic genre.
Let me disarm you, take you anywhere you want. So let me, there's an army I'm fighting around your heart. Let me disarm you, 'cause baby I just wanna love who you really
Our project has three major components. We have our microcontroller kit, our logic board, and an ancillary circuit for biasing our audio signal, as well as our LED matrix. Our LED matrix is composed of 64 red LEDs, which are configured in an 8x8 manner. They're multiplexed, which means that the columns all have the same connection to their anodes, and our rows have the same connection to their cathodes. When we cause a source on a column and a sink on a row, that individual LED will turn on. In this manner, we are able to control each and every single LED individually. To control and power our LED matrix, we have a logic board composed of 6 registers. These 2 registers are 8-bit parallel out serial shift registers, which take a data or serial signal as well as a clock from our microcontroller. These 4 registers, which are placed directly in front of our shift register stack, are parallel access shift registers. They're being used as latches, and when given a clock signal, will set their current input as the new output, which is maintained until they're given the next clock or clear signal. As you can see, our microcontroller provides 4 signals through these orange jumpers to control our logic board and therefore the LED matrix. From left to right, we have our clock signal for our 4 registers acting as latches, a clear signal to all 6 registers to reset the entire board at once, a data or serial, as well as a clock signal for our shift register stack. Here is an example reading of all 4 signals. In addition to those 4 outputs, our microcontroller is grounded to the board to ensure the same reference for our signals. In addition, it takes one final connection, the input for our audio. The microcontroller's ADC, or analog to digital converter, expects a signal from 0 to 5 Hz, whereas our audio signal ranges from -V to +V, typically around 1 volt. Therefore, the ADC will only read the positive components of our signal. To remedy this, we use a DC bias circuit, which will lift our analog signal up 2.5 volts so that the entirety of the signal fits within the expected parameters by using a voltage divider as well as an RC circuit. Here we have an example audio signal as well as its biased one. Something to note here is that the amplitudes, as such, of the bias signal is consistently smaller than those of the input, as seen here and here.